Welcome to Summarize Science, where we break down the latest research. Modern artificial intelligence, from image recognition to language models, relies on deep neural networks running on powerful GPUs. But as we approach the physical limits of classical computer chips, researchers are looking for the next big leap in processing power. Many believe that leap will come from quantum computers. However, getting quantum computers to run complex AI models has been a massive challenge. Previous attempts often required breaking the quantum state between layers by measuring the result and feeding it back in, which negates much of the potential speedup. This paper presents a major step forward, the first fully coherent quantum implementation of a multi-layer neural network. This means the entire prediction process can run in one continuous quantum computation, preserving its power. As you can see in this diagram, their architecture is not just a toy model. It mirrors widely used deep learning structures, including key components like 2D convolutions, nonlinear activation functions, and skip connections. The researchers analyzed the performance under 3 different scenarios for how the computer might access data. In the most optimistic scenario, where both the input data and network weights are stored in a special quantum memory called coherent, the speedup is exponential. This could turn a problem that takes a classical computer years into one that takes minutes. Even in more restrictive scenarios without full coherent, they still prove massive speedups are possible. They show a quartic speedup, meaning to the power of 4 if only the network weights use coherent. And impressively, even with no coherent at all, their method still achieves a quadratic, or squared, speedup over classical methods. One of the key insights that makes this possible comes from a feature of classical networks known as a residual or skip connection. Classically, these connections help train very deep networks. The researchers discovered that in the quantum version, these connections are fundamentally essential to keep the computation stable and prevent the signal from vanishing. So, let's recap the major points. This work provides a complete blueprint for running inference on a modern, deep neural network coherently on a quantum computer. It establishes provable, significant speedups over classical computers across several practical data access scenarios. And it's the first work to coherently implement a multi-layer network with the nonlinear activations that are crucial for AI. This research provides a concrete path for integrating fault-tolerant quantum computers directly into modern deep learning pipelines. While the necessary hardware is still in the future, this lays the theoretical groundwork for dramatically accelerating the AI of tomorrow.